All right, so you drew side and an in view. Good job. What do you think the rake angle of your tool is? Any guess?
30 degrees.
45. Okay. 30. Okay. It's probably less than 45 would be my guess. Probably more in the 30 range. It's a little hard to tell though, because right around that end of the tool, it sort of curves and the angles are perplexing right there. How many flutes? 4 flutes. All right. What does 4 flutes mean on an end mill this small? Anybody have any idea? 4 flutes means steel. Why?
Chips.
Stress egg? that was good. I mean, it was a good guess. It's better than stress egg. So, yeah. So when you're cutting a material that is a lot stronger, you need a flute that is much more robust. If you have a 2-flute tool, they have 2 giant flutes on them, and they get thinner. So the 4-flute tool, the flutes are bigger, they're more robust, but the spaces between them, the gullets, are really small. And those small gullets means you can't remove a lot of material. Now if you're machining aluminum, we can hog out a lot more material, so we need a place to put a lot more material, and so we have to have a lot bigger gullets on the sides to contain all of that material until it turns far enough to throw it out. Yes, this is the giant foam end mill, which is excellent for throwing as well. But anyway, so yes, so for steel, on a tool this size, we would often use 4 flutes. On aluminum, old school would be 2 flutes, but now most often people will use 3 flutes, which is between 2 and 4. And one of the things that they do with that is that the 3 flutes are not evenly spaced around the tool. So instead of being 120 degrees apart, one of them will be like 125 degrees apart. And the reason that you do that is if you remember from lab or you don't remember from lab, but anyway, I have this tool and it is cutting along and it keeps cutting. The surface, if we look from above and we looked on a really small scale, the surface will look like this. Now, if we come back and we cut this again at the same feed rate, what will happen is these little sections are harder to cut than this section right here. And that will start an oscillation in the tool. And because the number of flutes, if we don't have an oddly spaced end mill, this oscillation will match the forces that are in the tool as it cuts the next layer. It will be getting thicker, thinner, and that will start to oscillate the tool, and that will end up as chatter. And so you'll get a really bad surface finish. So one of the things that you can do about this, you can turn the tool at a different speed, but one of the other things that you can do about this is put very uneven tool spacing, or tooth spacings, so that you get different height and different width between all of those little cusps that are left over. And that makes it so you can't build up a resonant frequency. I say you can't. It's less likely that you build up a resonant frequency in your tool, so you get a better surface finish. How deep an axial cut could you take with your tool? 1? Are they 1 inch? Okay. Yeah, so it's just up to the end of the cutting edge, not to the end of the gullet. So the gullet goes up higher than that, but the cutting edge, you'll see a place where that grind stops. That's as deep as you can go in a single pass. In general, we don't want to go that deep. If we go that deep, we have to have a really shallow radial depth of cut. Total length, that's fine. What was anything that you noticed on the flutes of the end mill? What were some features that you saw on the flutes of the end mill? There are all kinds of things going on there. What?
Gullets.
Okay, there were the gullets behind it. All right. What else? Yeah.
It's just, okay. The way the end is cut, where you have two that go all the way to center, and
Okay.
two that do not go all the way to center.
Yeah, so we have two that go to center. I may draw this backwards, but anyway. It kind of looks like this with two that go to the center, and then there are two more that don't go to the center. So, end mills do not, there we go. End mills do not like to plunge because they don't have they're flat on the end, so they don't have a good way to get rid of the chips when you plunge them. But if they do have these flutes that go all the way to the center, or these teeth that go all the way to the center, they can be plunged. However, when we do it, we want to move the tool sideways as we plunge. We want to ramp into it so that we're helping the chip to get, or the tool to get rid of its chips. If you just plunge straight down, it won't work very well. One problem that we have is that the velocity, so the cutting edge out here is traveling really fast. The cutting edge right here is traveling slower. And the cutting edge right here, because the radius is so short, is just barely moving. And right at the center, it's not moving at all. And so that's another reason that the center is really bad at cutting. So if we need to plunge an end mill, we want to ideally drill a hole first or ramp in as we cut. What else did you notice on the tool?
There's some really cool, like with the actual edge of the flute, it's backed by a lot of material and it's raised. So there's an absolute point where it touches and it actually cuts the material. But
Yeah.
just underneath that, there's a lot of material backing it, so it pulls the rigidity of the tooth of the flute.
Yeah. So there's a ton of material right out here, right on the tip. The length from here around, it's just got a bunch of material, big and beefy, trying to support it. And this little tip right here will cut the majority of the material. Now all of these that I think that I handed out are flat end mills, so they have a sharp corner right here. There's another kind, which this tool is made to represent on this end, which is called a bull nose, and it has a little tiny radius right here. And these are really good because I've taken this, the most common failure point is that little tip sticking out, and I've made it into a nice radius corner so that it is big and beefy and strong. The technician, 3 technicians ago, called these end mills with the corners pre-broken off for you. So anyway, but they're precision broken off. So that helps out. There's also, right behind the cutting edge all the way down the flute, you'll notice a little flat. There's a land right there. That land has a couple of points to it. One is that it is making the very sharp edge on the front, but the other is that it actually angles back a little bit. So it's super hard to see, but if we had this cutting edge right here, and we could look at it on a microscopic basis, it doesn't go horizontally across, it angles back just a little bit. Why does it angle back just a little bit?
So it doesn't rub.
So it doesn't rub, that's right, because as we cut the material right here, we're going to elastically and plastically deform it, and as soon as we get to right here, we're no longer holding that stress on it, so it's going to elastically recover. So here again, in a little tiny space, we have to have room for elastic recovery so that we don't rub the tool and just create a lot of heat. Okay, great. Maybe I'll take those back before you start using them on each other or something. Before you start.
You're just giving us ideas now.
Nikki gets so angry when people machine the tables in here. No, it is.
It's so satisfying.
Yo, oh my god. That drawing's crazy.
It's really good,
Thanks,
yeah.
it's always
The what?
the questions. We did answers too. I did that.
But we went ahead because I figured it was gonna be a while. All right. So how do we do this? What happens when we get a tool like that and we need to figure out what cutting parameters to use? The tool manufacturer will give us the cutting speed in surface feet per minute, which seems unhelpful. But the reason that they do that is because surface feet per minute is what the tool is capable of doing. It is independent of the diameter of the tool that you're using and the number of flutes. So it works for all of the tools that are of the same material. To get to RPM, this is one of the few calculations that we will actually do. So RPM is 12 times the cutting speed over pi times the diameter. The units in there are funny. The 12, the purpose of the 12 is to convert feet to inches, so you don't have to do units conversion. It's already in the equation. If you're in the lab, 12 over pi is about 4, so you can estimate it as 4b over d when you're trying to figure out this in the lab and you're not allowed to have your phone, or somebody stole your phone, or you dropped it in the coolant tank or something. 4b over d will do that. Or your hands are super nasty with coolant and you're like, I'm not grabbing my phone right now. So then the tool manufacturer would give us information. And really unhelpfully, when they give you this information, they either give you feed per rev or they give you feed per tooth, and they're often really terrible about telling you which they gave you. So they often don't have units on it. So they will almost always have a sample worked, so you can look at the sample and see if you have to know the number of teeth or if they've already included that. So the thing that we need to tell the machine though is inches per minute. So inches per minute is the machining feed rate, F sub m, and that can be the feed per rev times the RPM, or if they give us feed per tooth, then feed per tooth times the number of teeth gives us F rev, and we can put that feed per rev and we can put that into the previous equation, as is shown down here on the bottom. So machining feed rate is feed per tooth times number of teeth times the RPM, and that kicks out inches per minute. All right? Not hard equations, and you can completely do them by units cancellation if you forget them. So, we often call feed per tooth the chip load. Chip load? but it is not. So it will often be used on the shop floor as the discussion of what is your chip load, and people will often talk about the feed per tooth. Technically, that may or may not be right. It is what is commonly used. The reason that it might not be right is if I am machining along the edge of a part, so I'm doing contouring, and I have a very small radial depth of cut. Look at this. This is conventional. That's crazy. So if I have a very small depth of cut, this calculation, the feed per tooth, gives me this distance right here, which is it's the amount that the tool has moved forward when the next tooth starts or comes around to cut. In fact, the load that the tool is carrying is over here, and it is a smaller number. However, it is super not easy to calculate. It almost has to be done, well, I mean, you can calculate it, but it essentially has to be done by modeling it, and so people just use feed per tooth instead. All right. That was more than we wanted to know. When we are cutting, this is a picture of a lathe, but it works the same way. Oddly enough, it works the same way with an end mill. So when we are cutting, we will, on this picture, this is a lathe, so the material is up here and is rotating around. And we have the tool right here. The tool is feeding across sideways at a constant speed. Well, as the material comes past the tool at a particular point in time, if we were to watch that specific point on the part, by the time it rotated all the way around and got back to where it's being cut again, it will have moved over. The tool will have moved over this far. Yes?
Sorry, just one more time, is climb, like, you have the tool on top and it's going this way?
So, the thing to think about is it thick and then thin, or thin and then thick? So, in this case, I know it's hard to tell here, there's the tool, and the tool always operates clockwise as viewed from above. Anyway, and so this is starting thin and going to thick. So this is conventional. If we were cutting on the other side, or there are lots of other ways that you can get there too. And so we have this is coming in and it starts thick and then goes to thin. That is climb.
Okay.
All right. So there's a funny thing about this. The standard is that tools turn clockwise. So here I am turning this tool. Anybody see a problem? No. Let's go for a bigger problem with this clockwise rotation.
Counterclockwise.
It's counterclockwise if you look from the end of the tool. So the definition of tool rotation is that you are sitting inside the motor looking down at the tool, and then it turns clockwise. They had to choose something as the definition, so they chose the motor. Anyway, whatever. All right, so we have this point on the stock. When it comes by the tool the first time, it is right here. By the time that it goes all the way around and comes back, the tool has progressed this far. That will leave this little cusp behind on the surface of the material. This also works with end milling. In end milling, it is based on this tooth comes by and cuts the surface, and then by the time the next tool enters the surface to cut it, the tool will have moved over a certain amount. And so it will leave the same shape with these little cusps on it. So to determine the theoretical feed rate, or surface finish, that peak to valley, so the height of these little cusps will be the feed, that's the amount that it stepped over, this distance that it stepped over squared, divided by 8 times the tool radius. So, if I want to have a smoother surface, I can move the tool more slowly. I can rotate the part faster so that it doesn't move over as much by the time the part gets back to the same location, or I can feed it across more slowly. Yes, question?
When you look down at the motor, is the tool going counterclockwise or clockwise?
So when you're sitting in the motor, looking down at the tool, it's going clockwise. When you look at it on the board for thinking about cutting something, you just draw it as clockwise. The thing that's confusing is if you ever happen to stand there and look at the end of the tool, it turns counterclockwise. But just be the one holding the tool. Don't be the part, be the machine.
And then
Some days you're the pigeon, some days you're the statue, some days you're the tool, some days you are, some days you're the part, some days you are the machine. Be the machine.
And then for the better surface finish, it's rotate the tool slower and then lower the.
Well, you could rotate the part or rotate the tool slower. That just loses money, and we don't want to do that. So we could feed the tool more slowly. Okay, that works. We can feed the tool more slowly, but we don't get as much done. So the other thing that we can do is get a larger radius tool. So if you were to actually machine things with this giant foam tool, then we would have a really smooth surface, assuming that it wasn't made of foam. By the way, speaking of foam roller manufacturing processes, did you know that they're made by extruding a center core and then they extrude an outer core on the outside afterwards? I didn't know that, and I started cutting this one up to make an end mill, and on this end it was all splaying open down here because they had not gotten good adhesion between this outer and the inner core. And so I had to go back and glue them all with odd foam glue. So that's why they're weird snot colored things on the end of my tool. Too bad, sad. Okay, f squared over 8r. We can make either of those changes. There are reasons that we might choose one or the other. What are the notes about? Yeah, okay. We'll do this as a review. What are the effects of changing rake angle? If we increase the rake angle, what does it do?
Increases heat and friction. Oh wait, no, that's decrease.
Yeah.
So.
But you're right. It's just that it does the opposite of that. That's right. We increase the rake, it decreases the heat, it decreases the normal on the tool, so it also decreases the friction. So if we want to create more heat, we stand it up to a neutral or even go to a negative rake. Primary sources of heat in chip forming.
Friction and shear.
Friction and shear, that's right. Friction, we're doing a lot of work on the material, and the material is trying to do a lot of work on the face of the tool as well. So friction and shear. How can we control heat most effectively? Slow down, okay.
Rake angle.
We could change the rake angle, and
Stressing.
we could reduce constancy of volume. We could reduce the friction. So that's the primary thing that coolant does. Well, actually, coolant does two things. Oddly enough, it does very little to cool. Coolant primarily puts a lubricant on the surface to reduce friction, and it works to wash away chips, to get chips out of the way so that we're not remachining them. It does a little bit of cooling. However, its cooling rate is so slow, and it doesn't happen right at the cutting location because it can't fit there. It gets squeezed out of the cutting location, so it doesn't do a good job of cooling. But it reduces heat by reducing friction. What is the primary source of thrust force? That's what's pushing the tool up out of the material. Friction on between the chip and the face of the tool. Shear angle increases with, sorry? Which way? Yes, so if I make the rake angle more positiver, the shear angle also becomes more positiver, which means the shear length gets shorter, which means less work is done, which means we have less heat. So many things going on. Excellent. How do we control tool life? Speed first, speed rate second, depth cut, not really. Yeah, nice. Yep, we just talked about that. All right, so how do we do this in real life? This is what it looks like when you get a tool chart. So you are going to machine a mold in your tooling class in 461 next year, and you're gonna decide, I wanna use this crazy tool that nobody else in the department uses, and we'll say, great, tell us how fast you wanna run it, because you're gonna have to enter that into the process planner. And so the way that you would do that is from a chart like this. So this is for Dataflute, which is a company that makes just standard in mills. And we can see that if we're cutting an aluminum, so cutting an aluminum alloy like 6061 or 7075, it says that our surface feet per minute is 800 to max. How do you feel about that?
That seems unhealthy. Why am I always the like? I feel very like average.
Quarter-inch angle, that is ripping.
Yeah, well, surface footage though. So surface footage of 800 mean that's not RPM. That's surface footage. So it just depends on the material that you have for the in mill. So 800 to max. Max means as fast as your machine goes, or as fast as you want to go, or we know that max means as fast as you want to buy new tools. That's why they tell you max, because they're like, yeah, bring it on. Turn that sucker fast and send dollars. Give us your credit card and here we go. We're off to the races. All right, so that's what they want to do first. Then the next thing that you do is you look for the size tool you have. So earlier the tools I handed out, I think they're 3/8" tools. So we would be looking right here. And there are 3 options, S, HP, and LP. S is slotting. You can see here, it gives you some ideas. Like if you're doing slotting with this tool, the axial depth can be up to 1 diameter deep. So if we have a 3/8 tool, it says your axial depth of cut can be 3/8 of an inch, and then your radial width can be half the diameter, but we know we shouldn't machine at half the diameter. We know that we should machine at 66%. So you can actually fudge that a little bit, just don't tell them. Be really quiet about it. And so you choose one of those 3. You say, okay, I'm slotting right through the middle, or maybe I'm just cutting along the edge, and that will give you a mystery number. That mystery number is either a feed per tooth or it is a feed per rev. And so what we can see is down here, they have calculations. And so if we're going to look at this bigger, say we're doing 3/8" deep slotting with a 3/4 inch end mill. So we're going to go to a bigger example here. 3/4 inch end mill. We have these 3 things. We're doing slotting, so it gives us 0.0068 as the number. We don't know if that is 6.8 thou per rev or thou per tooth, but if we calculate it out, we would use the spindle speed is 12V over pi d. That gives us 4,000 RPM. We then put it into this next thing. It turns out that it's feed per tooth on this chart, so we have to multiply it by 3 teeth per revolution. And we get 83 inches a minute. And when we look at that, this also has a horsepower calculation, so we can find out that the horsepower at the tool requires 5.84 horsepower. However, there are inefficiencies in the machine. So down here it talks about these inefficiencies in the machine. It has an 80% efficiency, which is what we use for aluminum. And so we divide this by 0.8, and this says that it's going to take, the motor has to be 7.3 horsepower to be able to make this cut. If we make this cut at 3/8 of an inch deep, and we're slotting. So the question is, can we do this? Well, with the new machines that we have, yes. But if we were to use the machine that's over in the corner that we haven't turned on yet while you've been there, I mean, it's been on, but we aren't using it yet. That mini mill has a 7.5 horsepower motor. So it seems like we should be able to do it. However, on that drawing, or on that, one of these directions, we were turning at 4,000 RPM. And when we look at the horsepower curve at 4,000 RPM, we only have, horsepower's over here, we only have 5 horsepower. So we can't do it. And if we tried to do that cut, the machine would go, and then it would stop, and then we would have a tool stuck in the middle of our part, and dogs and cats, and all kinds of bad things. I can think of other bad things, but we'll just leave them. It's election. All right. Nothing at all. So anyway, we would not be able to do that. So what would we do in that case? We would have to reduce our step over. We would have to reduce how deep we were cutting, or we would have to turn it more slowly, and both of those might help us out in that calculation. So, all right, we could do that. So here's what we end up doing with these tools. We talked about the fact that as we cut, the strength of the material goes down as the temperature increases, but the temperature is going up very quickly as a higher cutting speed. We need materials for our cutting tools that have a very high toughness. They need to absorb all of those impacts. They have to have a very high hardness. They need to be able to get the heat out of the tool or out of the chip, get it away from the cutting face so that they don't break down. It seems like we're just lost here. It seems like we have no hope. But we do have hope. So we have hope because there are lots of kinds of material we can use. We could use tool steel. We're not going to use tool steel. Nobody uses tool steel anymore. We could use high-speed steel. So the tools that I handed out were high-speed steel. High-speed steel, the good point is that they're cheap tools. The other point that's really good about them is that they are sharper than any of the other tools until you get to diamonds. So in anything, any normal tool, high-speed steel is the sharpest that you can get. And that's because the size of the molecules is smaller and more even, and so you can sharpen them to a finer edge. If we wanted to do this, they're really bad on friction, so we would need to put a coating on it. We can put this coating on. The coating is like 10/1000ths of an inch thick or thinner. It's odd that it makes such a difference with just that little tiny coating on there. So let's say we wanted to buy a 1/2 inch end mill of that. A couple of years ago, to do that would have cost us $19 if we just got the end mill, and up to $26 if we got a coating on it. All right, that's not bad. Most of the materials that we use are actually made of carbide. So carbide is a material, it is tungsten carbide. We'll see it in a minute how they make that. But it is a very tough material, and it has much better heat hardness. So it is like 10 times better on the speed that you can run it than high-speed steel. You lose a little bit of toughness, but not a ton. You can't make a really sharp edge because it will break off, and that's because the material is pressed together, so it is not quite the same bonding as happens in other materials. And you can coat it to make it exactly as you want it. If we were to look at carbide, there we go. Remember that high-speed steel was $19. The carbide tool will be $40. So you double the cost, but you get 10 times the speed out of it for the same tool life. That's nice. That seems good. But coating it costs way more money. Way more money. We tripled the price of it, or doubled the price of it almost, by putting a coating on it. And that's just because it's harder to get the coatings to adhere to the carbide. Still worth putting a coating on it, but anyway, it makes it a lot more expensive. Okay, so yeah, let's look at carbide. Excellent. Turn your in-mill paper over. Insert. You need another? I'll give you one or two. All right. Okay. So this is an insert. It could go in a lathe or it could go in a mill. It goes in a little pocket that you mount it into. And we're going to assume that it is headed straight out. So the holder is neutral. So the holder will not add or remove a right angle as you look at this and you try to understand what it looks like. So you're going to draw 3 views of it, a top, a side, a top, a side, and an isometric. So if you're in a team of 3, then each one of you should draw one of the views. If you are in a team of 2, then you can share. And I want you to kind of answer the same things. I want to know what surface features you see on it. I want you to figure out if it seems sharper or duller than the in-mill that you just worked on. And answer these fine questions.
Not quite.